Okay, welcome back. So now I finished last time with explaining the decomposition of the Riemann tensor into its three parts, and I made these comments that in the two-dimensional case there's really just one part that's the scalar curvature part, and the two other components are zero. The only part is the Gauss curvature. And in the three-dimensional case, there was still only room, because there's just three different indices possible for the U part and the V part, the traceless Ricci and the scalar curvature part, and the Weil part has to be zero. So in that case, one can express the Riemann tensor in terms of the Ricci tensor completely, and therefore we can control everything in terms of the eigenvalues of the Ricci tensor. In particular, we can compute all the sectional curvatures in terms of the Ricci tensor. So let me make a few more comments on this in higher dimensions. So remark number 3 is that in four dimensions, this is of particular interest in physics, because when you have a Lorentzian metric rather than a Riemannian metric, you can make the same decomposition of the Riemann tensor into these three parts. So if the metric G is Lorentzian, then from a physics point of view, in physics, metric with U and V both equal to zero, in other words, the Ricci tensor completely vanishing, is a model for a vacuum spacetime. And in this case, all the information there is in the Weil tensor. So all the info is then in the Weil tensor. Say, information on a black hole or on gravitational waves. Black hole, geometry, or gravitational waves. So in that particular example, where you have a vacuum spacetime, all the interesting physical information is contained actually in the Weil tensor. So the Weil tensor has a crucial physical significance in the four-dimensional case, and the fact that it is conformally invariant, for example, has to do with the fact that the light cone structure is independent of conformal changes of the metric. So that's one particular interesting example in the four-dimensional case. I want to make another remark on the four-dimensional case. In the four-dimensional case, you have one more symmetry coming from the Hodge dual between two forms. So in case n equals 4, there is an extra symmetry star, which sends two forms into two forms, namely sending omega into the volume form. What's the notation here? Where you insert omega gives you another 2 form, and then you can look at the decomposition of this space with respect to the star operator, and this gives that W can be decomposed into W plus and W minus, giving you one more symmetry, but that is special to 4 dimensions and will not play a major part in this section of our course. What's more important is that the decomposition into these components of the curvature tensor gives us important examples. So one example is the Einstein manifolds. A manifold is called an Einstein manifold. MNG is Einstein if the Ricci tensor is a multiple of the metric. In other words, if V is identically 0. V identically 0 are the Einstein manifolds, and this is only interesting, of course, in the case n equals 3, because in n equals 2 this is automatically true, as we have seen. So for n greater or equal than 3, something special happens because of the second contracted Bianchi identity. So there's a little lemma. If n equals 3 or greater and V is identically 0, so we have an Einstein manifold, then it follows that the scalar curvature is constant. And this simply follows from the fact that if we differentiate this up there, then we get, take the divergence, then we get gradient I Rij is equal to 1 on n, gradient J R. But on the other hand, by the second contracted Bianchi identity, this is equal to 1/2 gradient JR. So if n is not equal to 2, it implies that the gradient of R is 0. So the Einstein manifolds also have the special property that the scalar curvature is constant. And a special, even more special subclass are the spaces of constant curvature. The spaces of constant curvature, we have both V identically 0 and W identically 0. In other words, only U survives. Now these are of course also Einstein, so that's the Riemann tensor has the form 1 over n minus 1 times some fixed constant k times gik gjl minus gil gjk. In other words, we have just one single fixed constant k that determines the whole curvature, and then the prime examples are of course the sphere and hyperbolic space and Euclidean space. And it's a famous theorem that if you have such a curvature tensor on the whole manifold, then locally the manifold is exactly isometric to one of those spaces. So theorem, then MNG is locally isometric to either Sn or Hn or Rn, where you have to take Sn and Hn with the right scale corresponding to the curvature K. Okay, so much for an introduction to Riemannian geometry. I see I have pushed this far up, so I put the board back down, sorry. This is the setup of notation that I wanted to do at the beginning. And now we are ready to define Ricci flow. So, we are given a Riemannian manifold, smooth. Most of the time it will be compact, but we will also have some non-compact example, but we will not deal with manifolds with boundary. So, Ricci flow. The task we're given is, so given Mng, a smooth Riemannian manifold. Let's call this matrix G0, smooth Riemannian manifold. It could be compact or complete. Certainly without boundary. And then the task is find a family G of T of Riemannian metrics, smooth family I should have said again, such that ddt of the metric at a point x and at time t is equal to minus 2 times the Ricci curvature at that point and time and for all x and for all t greater than 0 such that Gij at time 0 is G0 Ij at x. Let's call this Ricci flow. Now, why would that be a good idea? Why might this be a reasonable equation to look at? The first comment is, remember that I wrote in the last lecture this Taylor expansion for the Riemann metric. So, remark, the Taylor expansion of Gij in normal coordinates was that Gij at x is given by delta Ij minus 1/3 Rikjl times xk xl plus lower order terms. Now, when you compute from this the coordinate Laplacian, so you compute let's call it Laplace coordinates of Gij, which is say G PQ second derivatives with respect to xp xq of Gij, then you just get things that come from here. And differentiating this gives you just purely these terms. So you get here, in fact, because of this symmetry here, you get minus 2/3 of Ricci because of taking this trace, Ricci Ij plus lower order. Or put it the other way, we see that this term minus 2 Ricci on the right hand side of our evolution equation is nothing else as 3 times this coordinate Laplacian of Gij plus lower order terms. So the leading term is 3 times Laplacian. In other words, what we have here is ddt of Gij is 3 times Laplacian of Gij at this local level. So it means that this is like a system of heat equations. And a special system of heat equations at that, because it seems to be treating all components in the same way. There seem to be sort of the same diffusion rates for all the components of the tensor. So it seems to be same diffusion rates for all components, and it seems to be that it's diagonal in the sense that the evolution of the Gij component seems to be just depending on the second derivatives of the Gij component, not of any of the other components. So there seems to be some important decoupling at the top level. So it seems to be so diagonal in this special sense. On the other hand, of course, this is only an approximation in normal coordinates. In reality, the Rij, when you look at the Christoffel symbols, which the Riemann tensor involves squares of the Christoffel symbols. So this is, of course, on the right-hand side, only linear in the second derivatives. It's nonlinear in the first derivatives. So this is a quasi-linear system. Not a linear system. Quasi-linear system of PDEs. So this is what one can say immediately by just looking at this Taylor expansion. So the motivation is that you have something which is nice in a certain way. It's like a heat equation. So hopefully this flow, this deformation, is going to make the metric better. Whether this hope is justified, we will have to see. That's the content of this course. We want to study the properties of this flow, and we want to see whether it is true that this flow can somehow improve the Riemannian metric. And it will turn out, as you probably have read already, that yes, it does improve it tremendously, and it is possible to improve the metric so far that even if you didn't know what kind of metric it was before you started, accept some local properties of the metric, that at the end you end up with something so nice that you can completely recognize what it is at the end, and therefore know what your original geometry was diffeomorphic to. So before we come to that, let me write down how the solution would look like in this particular example of Einstein manifolds that we had on the board before. Because it turns out in the case of Einstein metrics, we can explicitly write down what the solution of Ricci flow is. So if the initial metric G0 is Einstein, in other words, if Ricci tensor at time 0 of the metric G0 is equal to some fixed lambda times the metric G0, and we know from here this lambda is going to be 1 on n times r, which is a constant by this little lemma that we have proven. Then we can simply set g of t to be the metric 1 minus 2 lambda times t times g0. And we can compute that in this case ddt of g of t is equal to minus 2 lambda g0, but minus 2 lambda g0 because under scaling of the Ricci tensor with lower indices, nothing changes. So this is just the same as minus 2 times the Ricci curvature of G0, but under scaling this doesn't change, and it's minus 2 times the Ricci curvature of GT. So this is the solution. Don't get confused by the scaling, right? So the Ricci curvature with both indices down does not change under rescaling the metric. The Ricci curve, the eigenvalues of the Ricci curvature you get by raising one index, and raising one index means multiplying with the inverse of the metric, means multiplying by the inverse of the metric, and then you get the correct scale. So this is the solution in this case, and you immediately see what it does. So if lambda equals 0, in other words, if we have a Ricci flat metric, then it doesn't move. So the Ricci flat metrics are, of course, fixed points of the flow. And lambda less than 0 means that this factor is getting bigger and bigger, and the metric just expands. So you get expansion for all t bigger than 0. And if lambda is less than 0, then you get that the metric contracts, gets smaller and smaller, lengths contract, and in fact you get a contraction on a finite time interval from 0 to T max, and T max can be computed. It is 1 over 2 lambda, which we know is equal to 1 over 2 lambda is equal to 1 over r, the scalar curvature of the initial metric, times n over 2. It's certainly less than infinity, and the curvature blows up like 1 over the remaining time. So here we have a very clear example, and this of course applies then also to the spaces of constant curvature, so we know that the sphere contracts to length 0 in finite time, and we get that hyperbolic space expands to infinity in infinite time. Now, what is the plan for the course? Let me make a quick summary of what I want to do. Plan of the course. I want to start with some basic properties and techniques. So this means in particular we have to use regularity estimates. We want to prove interior estimates and curvature estimates, estimating higher derivatives in terms of smaller derivatives, so on. For this we will use maximum principle. This will allow us to get a criterion for extending the metric in time. For example, we will show that if the curvature is bounded, then the metric can be extended as long as the curvature is bounded. And then we want to look at the three-dimensional case, the original paper of Richard Hamilton, Hamilton's result on MNG with Ricci curvature positive. It's the famous original result from Hamilton 1982. Give a complete proof of that in a slightly modernized version. And then we want to develop techniques along there that have to do with rescaling singularities. The scaling of singularities will lead us to singularity models. How do singularities look like? In order to do that, we will have to take limits. Now, taking limits will need a compactness theorem. And now in this compactness theorem, there will be an issue. If the curvature is not positive, then you will not always be able to get a compactness theorem unless you have control on the injectivity radius. The injectivity radius in terms to control is very hard under the Ricci flow, and it was due to the great work of Perelman that it became possible to do this. So we need Perelman's work on entropy, non-collapsing, and injectivity radius estimates. Okay, so I think this is enough for this course, and I have given you various hints to the literature which you can also download from the course folder, from the material that I provided. I would in particular recommend for easy reading the notes of Peter Topping, and for some of the algebraic aspects, the book by Simon Brendle, but also the other references, like the original papers that I posted there, are definitely worth reading and checking. Okay. Now, I gave you sort of the simplest examples on Ricci flow already. Now, one particular feature of Ricci flow is the fact that the Ricci flow equation is invariant under coordinate changes. So notice that Ricci flow ddtr ddtg equals minus 2rij. Since both sides here with these two indices are symmetric tensors and transform in the same way under coordinate transformations, this is invariant under coordinate changes. Once you have a solution of this equation, it remains a solution in any other coordinate system. Now, this allows for the possibility that you may have a solution of this system of equations that simply comes from the fact that you have changing your coordinate system, and that's why the metric is changing. Obviously, this would only be possible if sort of the right-hand side, the Ricci curvature, is exactly looking like it comes from the change of the coordinate system, and the change of the metric under change of coordinate system is given by a Lie derivative. So it could be that we have a solution of this equation which is not changing the geometry of the manifold at all. It is just a solution of this equation because the coordinates are changed in a way that is somehow compatible with the Ricci curvature of the manifold. And this leads us to the concept of so-called Ricci solitons. And this is the first thing we explore now. Okay, Ricci solitons. suppose we have a Riemannian manifold. Again, suppose that in addition to the metric, we have a vector field x of t, depending on time, and a family of Riemannian metrics G of t. Now, if we have such a family of vector fields, then there is a corresponding family of diffeomorphisms. So that phi of t so this is the corresponding family of diffeomorphisms. In other words, we have that the derivative of phi of t is just the vector field x of t, such that for some function f on the manifold we can compute that ddt of f at phi of x and t is given by x at phi of x and t, comma t, applied to the function f. That's what this means. So we have a vector field and we have a family of diffeomorphisms, and then if I set a new metric g tilde to be the pullback of g of t under phi, g tilde of t to be the pullback of phi star of t of g of t, then we can compute that the derivative of g tilde at t is, on the one hand, phi star of the metric derivative, and on the other hand, plus phi star of the derivative of the metric, and the derivative of the metric is the under this vector field x is the Lie derivative plus phi star t of the Lie derivative in direction of the vector field x of g of t. So now, if we then set that our metric g of t, just fix it for a moment, g of t is just the initial metric, g naught, and if the vector field x is such that the Lie derivative of the metric G0 is nothing else but minus 2 times the Ricci curvature of G0. Then, because this is fixed, the first term vanishes, then we get that ddt of the pullback metric, G tilde of t, is just equal to phi star of minus 2 Ricci of G of 0, and G of 0 is equal to G of t, so we get minus 2 times Ricci curvature of the metric G of t. And this solves Ricci flow. So if we find this situation to be true, then you get a solution of Ricci flow. And this means we could have a metric which doesn't change at all. It's not really, the geometry is not changing, but we're just sitting at different points of the manifold. We're changing our coordinate system, and as we change our coordinate system, we change the metric according to the formula that is given by Ricci flow. Let me give an famous example. This example was studied by Richard Hamilton, and he called it the cigar soliton. It will become clear in a moment. But it also plays a role in physics. Ed Witten studied this, and we called it a two-dimensional black hole. And this is due to an interpretation of Ricci flow as a first component in a renormalization flow, motivated from string theory. I'm not sure I can get to that in this course, but it's a famous example, and this is just a Riemannian 2 manifold where M2 is R2, and the metric G0 is just given by the Euclidean metric dx squared plus dy squared, scaled by the factor 1 plus x squared plus y squared. Now, when you compute for this obviously well-defined Riemannian metric the Gauss curvature, then you end up with the following numbers. You get 2 over 1 plus x squared plus y squared, and therefore this manifold has Gauss curvature tending to 0 near infinity, so it looks like a cylinder near infinity, and it's obviously for x and y close to 0, looks like Euclidean space, so it's closing up, so it looks like this. And that's where the name cigar comes from. And you can then set up the vector field to be minus 2 times x times ddx plus y times ddy. so it's pointing towards the origin, some color here, and pointing this direction, the vector field y, and you can compute that indeed the Lie derivative of g naught in direction of y turns out to be minus 4 times divided by 1 plus x squared plus y squared times g naught, and we know that the scalar curvature is twice the Gauss curvature, so indeed we get here the Ricci flow equation that we needed, and in other words, it looks like the metric is contracting. After all, it's positive curvature. It looks like the metric is contracting, but it's only contracting because we are moving closer to the tip here, and we're changing the coordinate system. The manifold itself stays the same. The total geometry is the same. We are just under this particular solution of Ricci flow looking at the same manifold in a different coordinate system because we're flowing with time in this direction. Okay, that is one example. Now you can make this is what is called a steady Ricci soliton. Because it doesn't change its shape at all, it's steady. Now you can also make so-called contracting and expanding Ricci solitons if you, in addition to the Lie derivative, allow the metric to scale. So if you said so if we set g of t is equal to 1 minus 2 lambda times t times g0. We have this situation for some lambda in R, lambda different from 0, and if you have that the Lie derivative of the metric in direction of the vector field g naught is equal to minus 2 Ricci of the metric g naught plus an extra term which comes from the scaling, and I have to look here, plus 2 lambda times g naught. If you do that, then you get again a solution of Ricci flow. Then again you can compute that ddt of g of t is equal to minus 2 Ricci Rij, where the term coming from the derivative of lambda t is compensated by the 2 lambda g naught over there. And these solutions are called expanding Ricci solitons if the lambda is, let me check my sign, if lambda is less than 0 and yeah, and contracting or shrinking, only if lambda is positive. And when we come to such examples a little later. Now, these solutions are often hard to visualize, so I would like to spend the last 5 minutes to give a comparison of this result for those of you who have studied a little bit mean curvature flow, and see that there are huge similarities between Ricci flow and mean curvature flow. Okay, similarities or analogies. In the case of mean curvature flow, you start in the simplest case with an initial map of a hypersurface in Rn plus 1, and you want to solve ddt of the position of the hypersurface is equal to the mean curvature vector of the hypersurface. Mean curvature vector. And it's well known in differential geometry that this is the same as the Laplace-Beltrami operator of the position vector, where the Laplace-Beltrami operator is taken with respect to the induced metric. Okay. Now, so again, you have a system of quasi-linear integrations that's the first, and it's again diagonal with this uniform diffusion I shouldn't say uniform, I should call it isotropic. Same diffusion in all directions. So these are major similarities with the Ricci flow system. And you also have the shrinking spheres. Simple exercise to see that spheres shrink to a point in finite time, so you have similar solutions. There's other contracting similar solutions, so for example there's curves that shrink under self-similarities. There's cylinders that shrink under self-similarities. So there's these self-similar shrinking solutions, just like in the Ricci flow case, and there's also a steady soliton. There's a solution, oops, this is not so straight. There's a solution which very much looks like the cigar of Hamilton. Was again also studied by Hamilton. he called it, in this case, he called it the Grim Reaper, for reasons I explain later. And the physicists also studied this in renormalization theorem, and they call it the hairpin solution. So again, a similarity that both the mathematicians and the physicists studied the object from a completely different point of view. And this has a solution. This is a solution which just moves under translation. Here it moves under translation, which means we are not changing somehow the coordinates on the object, but we're changing the coordinates in the ambient space just by diffeomorphism, in this case translation. And you have an explicit formula in this case here. You would have something like y equals minus log cosine of x plus t. And this is a solution which is translating. Check it out yourself that this is a solution of this system. And you should think of this translating solution for mean curvature flow as an analog of the steady Ricci soliton, which I call the cigar. And with this, I'd like to finish the lecture for today.